Hello and welcome back to our dive into graphing sine and cosine. This is our last day of this section. And in this video here, we're just going to do one example and one huddle problem. And that's using these trig functions to model real life data. One of the big uses of math is to take data points and use the function we come up with to predict the future or figure out what happens in the past. So here, example 7, sine and cos functions can model many real-life situations, including electric currents, musical tones, radio waves, tides, and weather patterns. So here in example 7, it says throughout the day, the depth of the water at the end of a dock in Bar Harbor, Maine varies with the tides. The table shows the depth in feet at various times during the morning. This is real-world data, comes from Nautical Software Incorporated. And we're going to ask to do three things. Use a trig function to model the data. Find the depths at 9 a.m. and 3 p.m. And then it says a boat needs at least 10 feet of water to moor at the dock. During what times in the afternoon can the boat safely come into the dock? It needs enough water. So let's look at our data. Again, this is real world data. You could go collect this yourself. We've got a graph here with our depth in feet and time values on the t-axis for time. Let's plot a few points. At midnight, it's 3.4, so that's going to be in between the 2 and the 4, a little closer to the 4, right about there. At 2 a.m., we get out of bed, go down there, and get the depth of it, 8.7. So at 2 a.m., it's between 8 and 10, but a little closer to 8, right there. At 4 a.m., we're a little more than 11 feet. So 4 a.m., we're right about there. Come on. Why is my pen giving me such trouble? 6 a.m., it's going back down. At 6 a.m., we're down to 9.1 feet. So here, just a little bit between the 8 and the 10. There we go. 8 a.m., we're down to just under 4 feet. So here's 8 a.m., we're just under 4 feet. Come on, there it is. At 10 a.m., we're at 0.1. 10 a.m., we're just above that t-axis. And then at noon, we're back up to 1.2 feet. So we do not have a full period, but we don't need one. If we can see here, we've got a peak. That's pretty critical, a peak. And then we also have a valley. So again, we don't have a full cycle, but we don't need a full cycle. And let me back up and show you something else here too. We want data for 9 a.m. and 3 p.m. Well, at 9, whoa, wrong way. At 9 a.m., we did not go down to the dock and take a sample or a reading, so we can figure out what that should be. And then it also said 3 p.m., right? Yeah, 3 p.m. Well, we stopped collecting data at noon, so we are going to predict the future. At 3 p.m., what is that water depth going to be? So again, this stuff is very useful in the real world. And let's get started here. And it says, begin by graphing the data. We did that. We can use either a sine or cos wave. It would just be a matter of different shifts. But let's use a cos wave. So here, y equals a cosine of bt minus c, and then outside the parenthesis a plus d. We got to figure out what the a and the b and the c and the d are based on just this data that we have. And they start us here. It says the difference between the max height and the min height of the graph is twice the amplitude. Remember, we've got a peak and a valley. Somewhere in between the peak and the valley is the baseline, because we go the equal number above and below that baseline. So an easy way to find the amplitude is we're going to take half of the maximum depth minus the minimum depth. Notice these numbers are coming off the y-axis. The deepest we ever saw the water was 11.3, minus the shallowest we ever saw the water was 0.1. 0.1. So if we subtract that, we get 11.2, and if we cut 11.2 in half, we get 5.6. That is our A value. And let me do this. I'm going to come here. Y equals A cos bt minus c plus d. What we just found was our amplitude, and that is 5.6. So we've got 5.6 cos, oop, that's a terrible S, that's a little better. We're going to find some number for b, I'll leave a spot for that, and then we'll have our left or right shift here, and our up or down shift out here. We'll work on that as we go. So we found the amplitude. Okay, what's next? The cos function completes half a cycle at which the times it had a max or a min. So if we go back to our graph, I'm going to use blue ink. Here's our max, and the time that occurred, I sort of covered it up here, was get back there, is at 4 a.m., and we had a valley, it looks like at 10. So 4 a.m. to 10 a.m. Again, we're going back to the x-axis or t-axis at this time because that would be half a cycle. We went from one peak to one valley. Remember, cos goes from a peak to a valley back to another peak. That would be a full cycle. So what we did here is we don't have the data to the next peak, so we can take the data we have from the peak to the valley and just double that. So back to here. The period, and I'm not going to just abbreviate that with a P, the period is 2, and then we're going to put in here these times. The time of the minimum depth was 10 a.m. minus the time of the max depth, or the max depth was at 4 a.m. And of course, we're going to do order of operations, grouping symbols first. That's going to be 2 times. 10 minus 4 is 6. So we get the period is 12, or 12 hours. So now remember, the number that goes in here, we divide that into 2 pi to get our period. Oops, let me go back here. Period equals 2 pi divided by b. Well, we just found the period. That's 12. 12 equals 2 pi divided by b. So let's solve for b. Step 1, multiply both sides by b. So you get 12b is equal to 2 pi. And if we divide by 12, we get b is equal to 2/12 or 1/6 pi. B value is pi over 6. So I can go to here. Our b value is pi over 6. Oops, wrong way. Okay, it looks like the only thing we're missing, well, we got a couple things here. This c value, our left and right shift, and our d value, our up and down shift. So let's go after that c value. Oops. Now remember, to find our left endpoint, if we've got the cos of something in parenthesis, to find the left endpoint, we set what is in those parentheses, that is bx minus c, we set that equal to 0. That's where cosine has its first peak. Well, our b value is pi over 6, and we're not using x, we're using t, and minus c is equal to 0. So if we add c to both sides, now over here c is positive. Ooh, and I forgot, we're supposed to plug in a time for t. So when does our first peak occur? Our first peak right here is at 4 a.m. So our time is 4. So this t becomes a 4. So that's going to be 4 pi over 6 is equal to c. And we can reduce that down to 2/3 pi. 2 pi over 3. So that is our c value minus 2/3 pi. Because this is a minus, that's part of our equation, and we're putting in there 2/3 pi. Now the final thing, I could put that into here. Oops, get back. Minus 2/3, we're only missing the d. Now this d, it's a pretty easy thing to figure out. It's your average depth. If I go back here, somewhere in between here is a baseline. How are we going to find the baseline? Well, it's the average. We're going to add the highest peak and the lowest valley, and we're going to divide by 2. So I guess I come back to here. And, I shouldn't be writing on this slide yet because that's part B. But we need our D value, and D is equal to the high plus the low divided by 2. So our high was 11.3. Our low was zero point 0.1. If you add those up, you get 11.4. Cut that in half, you get D is 5.7. Remember to find the amplitude we subtracted and divided by 2. Here we're adding and dividing by 2. So that gives us at the end here a plus 5.7. So there is our equation. We've modeled the real life data with a mathematical model. Okay, now we're going to fill in a gap and predict the future. Since we have this model here, if I go back to our original problem, they do ask us to find the depths at 9 and 3. 9 a.m. is just 9, but 3, we got to think about in military time or hours past midnight. That will be 15 hours past midnight. So if I come back to my model right here, for the first one, we wanted at 9 a.m., so I would just compute this, replacing the t with a 9. So that's going to be pi over 6 times 9 minus 2/3 pi all in there plus 5.7. So at 9 a.m., I would just bust out the calculator, and that turns out to be approximately 0.84 feet. Let's see if that looks good on our graph. 9 a.m. 0.84. So at 9 a.m. 0.84, if we look in here between 8 and 10, does our number 0.94 fit in there? Or 0.84, excuse me. Yeah, 0.84 is in between there. So that does make sense on our graph. Next, we stopped collecting data at noon. We're going to predict 3 hours in the future. So I would just take out the 9 and replace that with, what did I say? It was a 15. So that's 5.6 cos pi over 6 times 15 minus 2/3 pi, and add that 5.7 at the end. And we're going to get approximately 10.6 feet of depth. 10.6 feet. And does that make sense? Well, if we sort of continue the graph, we could sort of estimate and see how close we are. So there's part B. Now, the last thing they asked us to do, it says a boat needs at least 10 feet to moor at the dock. What time can it safely dock? Well, if we look at the graph, here's 10 feet. So when the graph bubbles above 10 feet, that means it's safe for the boat to dock. Now, if we have a good enough graph, we could just, bring these down here and we can estimate a little bit maybe after 3 a.m. or down to here between 7 and 8 a.m. But didn't it say afternoon? What times of day in the afternoon could it dock? So another way to solve this would be to take our equation here. Remember, this gives us the depth of the water. Y is the depth of the water. So we could set this equation, 5.6 cos of pi 6t minus 2/3 pi, quantity plus 5.7, 0.7, and we could set that equal to 10 and solve it. In the textbook, they use the graph and a TI-89's intersect feature to find those intersects. We could do that, or you could also use the solve feature in the F2 algebra menu. You could do solve. They give you a left parenthesis. You'd type in all of this, set it equal to 10, give it a comma, well, use t or x, whatever variable you used, and close the parenthesis. And that will spit out the times at which the water is deep enough. And the calculator, if we round it off, it's approximately 14.7 and also 17.3. 17.3. So remember, this is sort of military time, so you could think 2 o'clock 0.7 hours, which is almost 3 o'clock, or I think 0.75 would be 3/4, so that's like 2:45 p.m. The boat could come in and safely dock. Or past 12, this would be 5.3. Point 0.3 is almost a third, and a third of an hour is 20 minutes, so 5:20. So if the captain of a boat calls in and says, hey, I need at least 10 feet, you could say, come to the dock between 2:45 and 5:20, and you should be fine. The power of mathematics. So that's our one example. Here is a sort of practice problem for you. It is also real-world data from the U.S. Naval Observatory talking about full and new moons. Here the Y column is moon illumination. So 1.0, that is 100% illuminated or a full moon. 0.0 is a non-illuminated new moon. It's in the sun all day with the sky, so you never see it. So it says here the percent Y in decimal form of the moon's face illuminated on day X of the year 2009, where X equals 1 represents January 1st. Blah, blah, blah. Create a scatter plot of the data. Find a trig model to fit the data. Add the graph of the model to part B to the scatter plot. How well does the model fit? What is the period? And estimate the moon's percent illumination on March 12th. And I was nice and I figured out for you that is day 71 of the year. So pause the video and see if you can solve this. Start it back up. Ooh, and let me show you this here too. I'll leave this slide up for you here. You can pause the video on this slide. The period, the left end point, the A and the D. You know, your the amplitude and your vertical horizontal shift. So pause the video on this, see if you can figure it out, and then start the video back up. See if you got it right. Okay, here is my graph, and I'm going to put in some of the data points. On day 4, it was 0.5, so that would be right about here. On day 11, it was fully illuminated. I'm going by a scale of 2 here. So at 11 would be right about there. Come on, pen. There we go. At day 18, so that's 12, 14, 16, 18, we were back to half illuminated. Come on. Day 26, we're at 0, so that's 12, 14, 16, 18, 20, 2, 4, 6. Day 26, here we are. Come on, 26. Day 33, we're at a half, so that's 26, 28, 30, 32, 33 would be right in between. There we are. So that's 33. So this will be 34, 36, 38, 40, 40. We're back to a full moon. So there's our graph. Let me connect those dots. And unlike the harbor problem, we do have a full cycle. We could do a sine wave here. We could do a cos wave. We could do either. I'm going to stick with just a sine wave. So let's find A and D first. Those are pretty easy. A is 1/2, and we're going to do our high to our low. Our highest is 1, our lowest is 0. So our A, 1 minus 0 is 1, times a half is 1. A is 1. And then D is our average height, or our new baseline. That is 1/2 of the sum of those things. And since it's 1 plus 0, half of that is the exact same. So both our A value and our D value are 1/2. So do I have, I'm going to make a new slide here. Y equals A cos of bx minus c plus d. We found A is a half cos, and there's going to be something x and then minus something, and our d value is also 1/2. So there we go. Let's figure out next the period. Period equals 2 pi divided by the number b. And remember, in the bar problem, the dock problem, Bar Harbor, Maine, the period is double the time from a peak to a valley. So here we had a peak and here we had a valley. That was on days 26 and 11. 26 is a valley, 11 is a peak. So we're going to put in there 26 minus 11. 26 minus 11 is 15. 2 times 15 is 30. So P, our period, is 30. Let's put that in here. Period is 30 days. 2 pi, or 2 pi divided by B. So we'll multiply both sides by B and divide by 30. So our B value is 2 pi over 30, or that reduces down to 1/15 pi. B is pi over 15. So our B value is pi over 15. Last thing we need is that C value, our left or right shift. So remember, this is where we take sort of what is in the parenthesis, the bx minus c, and we set it equal to 0. And we found b was pi over 15. And the x value, we want to find the first peak since we're using cos. On what day did we have our first peak? First peak was at 11. So we're going to put an 11 in there. So that becomes an 11 minus c equals 0. Well, if we multiply pi over 15 times 11, that becomes 11 pi over 15. And we'll add the c to both sides. So c is 11 pi over 15. Go back to my model. 11 pi over 15. So here is the mathematical model that will give you the percent of the moon's illumination on any day of the year. You just pick the day and plug it in for x. So let's go back and see how much of this problem we've answered. Create a scatter plot. Did it. Find a trig model. Did it. Add the graph of your model in part B. Does it fit? It fits pretty well. We're going to sort of skip that. What is the period of the model? We figured that out. Our period, Yeah, we already did that. Our period was 30. I sort of erased it there. Period was 30 days. We go from a full moon to a new moon and back in about a month. Estimate the moon's percent illumination on day 71. So we'll go back to this model. We will take out that x, we will replace it with a 71, and we compute. I would just do it on a T99, and you get y equals 1.00. As a decimal, that is 100%. So on that year, we had a full moon on March 12th, 2009. Excellent. Very powerful mathematics. Ooh, and if there is a homework assignment for this section, it's a single page handout, or it might have kind of been this the moon illumination problem. And that wraps up section 4-5, graphing sines and cosines. I hope you had as much fun as I did. I'll see you in class.